Hi, I'm Daniel Graziano, and I'm going to be going over the details to my final project called Neuroscience and Neural Nets. To start with, our broad goal here is to explore the deep learning techniques as they apply to neuroscience datasets. The data we'll be looking at is electroencephalography data, also known as EEG data. This is a type of time series data. The techniques we'll be looking at are convolutional neural networks, a type of RNN called the GRU, the dense neural net classifiers, UMAP, and echo state networks. Our more specific goal is to predict digits that subjects were viewing on a screen using only their EEG signal. So let's take a closer look at the dataset. The dataset consisted of recordings made from various patients of a visual paradigm where the subjects view digits 0 through 9 on a screen, and the data is recorded from them while they do that. One of the recording systems, the MindWave, has the recording electrode in one place called the FP1 location on the frontal parietal lobe on the front of the head. The other recording device, called the emotive epoch, has multiple electrodes all over the head, as you can see in this bottom right part down here. The electrodes are located and scattered towards the front, back, center. Pretty much they cover the entire head. And we'll get a look at that equipment later so you can have an idea of what it looks like. The data comes in a text file, which needs to be parsed by Python, which we'll go through. But basically, the data has different fields, which is an ID field, an event, which distinguishes when a specific test happened. There's a device string, which tells you which device was used when. There's a channel string, which tells it what possible channel was being recorded from. You can see the channel codes are down here. An example of one is F7 or AF3. And the code is the target of our training data set. It's what the digit that the people were actually seeing when the recording was going on. The last two are the size data set, which helps us determine the sampling rate. It basically tells us the number of values captured in the 2 seconds. The recording sampling rate was not the same for every sample, so it's important to look at the size and adjust your parameters accordingly to normalize, and we'll get into that more later as well. And finally, the last part of the data set is the data itself. The EEG data is a string of numbers representing a time series data. Each of them represents the value of the EEG at a specific point. And we'll get into more about what EEG is and why it matters. So let's take a look at the data set here over in the notebook. We load the necessary packages, and then we can get into the actual data itself. You can see a picture here of the MindWave device. The data set is about 200 megabytes, so I went ahead and created a function to download the data from Google Drive. I've posted the data up in my Google Drive, and it can be downloaded via a publicly accessible link, which I posted here, so anyone can just download this using the function or using the URL directly onto their computer. The data is also available via this link. You could download it at the very top here. If you click on this link, you could download the dataset from there, but it's just a little easier to get from the Google Drive. Here's the summary that I already went through, and you can see that the first thing we did is we went through and we loaded our dataset into a pandas data frame. And we had to identify the names of the different columns that we just discussed. We noted that there was no header and that the white space was the delimiter. So there was no commas, it was just all white space. We verified the data was loaded correctly by using the head command, and we can see that the columns loaded in as expected. Getting back to the slides here. Before we go any further, I want to go through the environment we're using to analyze this data. Almost all of the data was analyzed using Google Colab, which was sufficient for this kind of data. It wasn't overly processing intensive. The only thing that required some extra power was training the echo state network, which required a lot of memory. So we used the P2X large instance on EC2, which was about 61 gigabytes, and this proved enough. The special packages we installed here were Swifter. Basically, that's a package to do the pandas apply operation, but distributed across multiple processors. So it's a parallelized version of apply. UMAP, which we'll demonstrate later. PyFFTW, which is a custom fast FFT algorithm, and the ECN model itself that we implemented. The data pre-processing steps we did is we first imported the data into the data frame, as you just saw. We converted the EEG into a NumPy array. We removed some trials where there was no digit present. We trimmed, we normalized, we calculated FFT, and then we split into train and test as we normally do. So I'll show you how that works now. Over here we see the first step that I mentioned, that we convert the data from a series of strings, you can see these are all just string values here, into a NumPy array, so we could actually perform operations. So this is where we use our Swifter apply operation that we discussed. We check if Swifter is in the modules. If Swifter is not available, it's not a problem. It will fall back and just use a regular apply, which is a little bit slower, but will still get the job done. We can plot a random EEG trace now from one of the trials to verify that we successfully loaded the data. So we just call a simple plot command here, and we can see that we have a nice 2-second segment of data. It doesn't look like much now, but we're really going to be transforming and analyzing this data and looking at it more closely. So later we'll make some sense of it. But for now, we just want to verify that it's there. We then filter out any of the codes that are -1. We're not going to use these. These are just random sample trials. The patient was not shown any number for the -1 code. So because there's no target assigned to -1, we just remove it. We then check to see the lengths of the different segments. We have a problem here. You can see that the lengths are all different values. This is not great for any machine learning application. We kind of want a nice uniform input into our models, so we're going to have to do something about this, some data cleaning. So we have a function here which goes through and trims the data down to the most popular minimum size. We will either pad or trim the data down so that we pretty much eventually end up with, as you can see down here, all the data is now a single size, which is 888 samples in this specific case. The trim data function works by trimming out samples that are not having very much representation, and the rest it actually trims them down to the smallest of the remainders. So we end up with data of the same size, and we perform a typical normalization calculation on each of the rows. Each of these consists of taking the value, dividing it by its mean, subtracting the mean, and dividing by the standard deviation, which is a pretty normal way to standardize data. And then we create the train and test split, as we mentioned before, with stratification, although the data set is very balanced, so it's not necessary to stratify if you don't want to. So we're going to get into a few more details about how FFT and spectrograms work, because that's so fundamental to how this project works. Spectrograms are a way of visualizing the spectral content of a sample, of a time series sample. Basically, the way this works is it's done using a fast Fourier transform, which transfers the time series data from the time domain into the frequency domain. So instead of your x-axis being time, your x-axis turns into frequency, as you can see from this diagram up here. So this calculation is usually done on a whole segment at a time, but that doesn't do much good for us. We want to get it to show where the spectral estimate is for any point in our sample. So we can do something called a spectrogram, where we take an FFT in a sliding window fashion. Basically, we can take an FFT and slide a window across the entire sample time, and we can create an estimate in chunks for our sample at different times. So we still preserve some time information by doing this, but we get an idea of what's going on in the spectrum at any given time in our sample. The result is a picture that looks like this, and you'll have time on the x-axis and the frequency on the y-axis, and the color axis that you see here is the actual relative power. So the more warm the color, the more red of the color here indicates greater power at that frequency as compared to other time bins or frequencies. So it's a kind of a 3D plot with the third dimension being color. So the takeaway message here, if all that seems too much, is the more warm the color, the more red the color, the more power there is at that point in the sample. So the first method we used was using convolutional neural networks to try to classify these, because these things are just pictures here. As spectrograms can be thought of as a type of image, with each of the kernels being a pixel. You could see on the right here, we have the type of model we used, and I can show you in the notebook as well. This function over here is what actually generates the spectrograms, and you can see we're taking in the data, and we perform the spectrogram using the spectrogram function as part of the signal toolbox, the SciPy signal toolbox. It takes in the data, performs the sliding window FFT calculation, and returns a series of frequencies and times, as well as the spectrogram, which is just simply an array. If you look at this data on its own, it's just an array of the different positions right here. And each of the positions has a number which corresponds to the heat map here. So the higher the number, the warmer the color that's assigned to it. That's all that's really going on here. We then apply this function to everything in our data frame so that we can make a spectrogram for every single one, using, once again, the Swifter module that we discussed before. We can then apply, yep, that's where we're applying it to everything here with the specified parameters. We are then checking our data frame here with the head command to see we have our original untransformed data. Now we have the spectrogram data too, which you can see, it's hard to see, there's two little brackets here which indicate that we have an array of arrays. So each of these arrays each of the data arrays in the spectrogram contain another array, which is a 2D image, or just a 2D collection of numbers which can be represented as an image. So now we're ready to almost ready to fit our model. We have another problem where, once again, the spectrograms are not all the exact same size. Again, even though we made the samples the same size, due to differences in sampling rate, remember all the samples are not sampled at the same rate, we end up with spectrograms of different sizes depending on the different sampling rates that are present in this large data set. So once again, we have to do a trimming normalization step here. And so we have this special function called spectrogram padder and zero pad. And this basically pads out the spectrograms to be all the same length so that we can perform our operations. So the spectrograms all end up being 25 by 85 by the time we're done with them. And this is good. We then define our model, which I was showing you before. It's a typical convolutional neural network. It goes through 3 rounds of convolution followed by a max pooling layer, and it does this with increasing sizes of neurons. After this alteration of convolution and max pooling, we enter the classification dense neural network, which is pretty typical. We pare down our neurons after doing some dropout all the way down to our typical classification last final output layer here called the dense, which is 10 because we have 0 through 9, so there's 10 classes. We have an activation of softmax for this so that we can accurately weight each target variable the same. We then feed this into the run model algorithm here, which goes ahead and builds the Keras model and runs it with a fit command here. It also does the train and test split for the data as we specified and determines the number of epochs in the batch size. So fairly typical stuff here. And then we have a separate plotting function here for plotting the accuracy as well. We then move down here to the, you can see the results of this. We train it and it goes for a long time. The issues we had here is that the data was not really well suited to this. As you can see, we don't really achieve very good accuracy, and the loss was less than stellar. We could see the loss never really changes for the test set, and it kind of plateaus for the training set as well. The reason we think this happened was because spectrograms are difficult to classify by convolutional neural networks. Convolutional neural networks map spatial relationships between real images in the real world. You could think of them like looking at a car tire or a bike. The pixels that are next to each other have spatial meaning. In a spectrogram, this is not necessarily the case. You could see in a spectrogram, the pixels are artificially generated, so just because the pixels are next to each other doesn't really mean that they have anything to do with each other. It's just a convenient representation of an array of the data. So because it's kind of an artificial image, it doesn't really do very well with convolutional neural networks, and I make that point here. Another issue is that spectrograms represent the summation of multiple underlying neural processes. The way a spectrogram works is we record EEG data, which is thousands and millions of neurons firing at the same time, and they oscillate at varying frequencies. We're picking up the results of those oscillations at the surface of the scalp. So instead of one of these pixels coming from a specific neuron or a specific unit, this is the summation of millions of neurons, so it's not a single unit. And this one next to it might be the summation of a million different neurons. So that lack of single unit, single pixel relationship makes it very hard for convolutional neural networks to do well in this kind of a setting. So that's why we think it didn't do very well. The second unit we looked at was the gated recurrent unit. We decided to look, I decided to look directly at the time series data in a raw format. The reason for this is that this type of recurrent neural network saves its memory state, and it's actually particularly useful at analyzing encoded sequences such as time series data. Time series often has influence from past points on future points, just as an influence on your past frame state, like what you're thinking of now, influences your future actions. So this memory unit built into GRUs really helps us work and classify with this type of data. We're going to take a brief break here because we need to split the video into 2 so it fits into 15 minutes. So please check out part 2 of this video for the rest of the summary. Thank you.